to study the pendulum using the Lagrangian mechanics. We'll start with the diagram here where we've got our pendulum bob, mass m with a rod length L. It's hanging from a fixed surface up here. We're going to define our coordinate system so that our origin is here where the pendulum rod attaches to the surface. So this is going to be the point x equals 0, y equals 0. So if x goes to the right, it'll be positive. If it goes to the left, it'll be negative. Y, we're going to assume by default is negative because it's dropping down this way. So when we go to set up our x and y components, x is going to be L sine theta, and y is going to be negative L cosine theta. So this negative just comes from the fact that y is dropping down kind of by default. This theta that we've already looked at here is going to be our canonical variable. So for the q in Lagrange's equations, this is going to be the q. It's going to be theta. Q dot will be theta dot. Now we sometimes call that an omega, but I'll be calling it theta dot. So your first goal when you're setting up a Lagrangian is to think about what the position vector is. So here I've got my position vector. You can always start in Cartesian components as x hat plus y hat. And if you need it, plus z hat. We don't need it today, but we might later. So we put in the trig definitions that we figured out just a minute ago. You can factor the L out of this to make it a little bit cleaner. The next thing we need is the derivative of this position vector, the velocity vector, because we need that for the kinetic energy. So we just take a time derivative of this piece here. The L comes along for the ride because it's a constant. And so sine becomes cosine, cosine becomes negative sine, and then we apply the chain rule because theta is a function of time. So this is a full-fledged derivative. We need to apply the chain rule. So everybody's going to spit out a theta dot. All right, so you have a cosine theta, theta dot, sine theta, theta dot. Everybody has a theta dot, so you can factor it out. So you can think of this piece here, the L theta dot, as being the magnitude of the velocity. And then this piece, cosine theta, sine theta, is the unit vector. We're now ready to set up the kinetic energy, the first piece of the Lagrangian. It's always 1/2 m velocity squared. You can always start with that. Going to equal 1/2 m, and then we take this thing and we get its magnitude squared. So I need to take r dot and dot it with r dot. So I'm going to take r dot, dot it with itself. The L and the theta dot will get squared because there's two of those combined in front of the r dots. And so now I take the unit vector and dot it with itself. I know that a unit vector dotted with itself is always 1, but it's nice to be able to verify it. So for example, when I have x hat dotted with x hat, I'll end up with a cosine squared. When I have y hat dotted with y hat, I'll end up with a sine squared. And the cross terms, anything that has an x hat dot y hat or y hat dot x hat goes away. It becomes 0. Lo and behold, I get cosine squared plus sine squared. That's going to give me 1. Just as expected, right? It's a unit vector, but it's nice to prove that it comes out to a magnitude of 1. And so we'll have our kinetic energy equal to 1/2 m L squared theta dot squared. And if you plug units into this, you'll have a kilogram meter squared per second squared. We usually call that a joule. To get the potential energy, we're going to use the sort of usual intro level MGH for the gravitational potential energy. You could do this with a full-fledged negative G m1 m2 over r, but this one works out just fine for our models. So this is going to equal negative mgl cosine theta. We're just plugging in what we had for y earlier, this negative L cosine theta. Now we're ready to construct the Lagrangian. You can always construct the Lagrangian as T minus V, kinetic energy minus potential energy. So we plug in the kinetic energy we got earlier and the potential energy we got just here. This minus sign goes away because it's always minus V. That's the combination that you need in order to work out Lagrange's equations. Once we have this Lagrangian, we can start constructing Lagrange's equations. I like to do this in 3 stages because there's sort of 3 pieces that you need. The first piece you need is the partial of Lagrangian with respect to theta dot. So we look at our Lagrangian here, these 2 terms, and we look for every term that has a theta dot. So this first term has a theta dot, and the second term does not. Remember, we have to treat theta and theta dot like they are separate, independent variables. Technically, they are related by a derivative, but in order for this partial derivative business to work out, we really have to treat them like they are separate independent variables. Just pretend like you've got x and y and you're taking partial with respect to x and partial with respect to y. So for partial L, partial theta dot, we apply the power rule, just drop the 2 down here, cancel those 2's, and reduce the theta squared to a theta to the first power. So that's going to give you this ml squared theta dot. You might recognize this as an angular momentum, right? It's going to have units of kilogram meter squared per second. You can also think of it as the moment of inertia times omega. That's intentional. The derivative of L with respect to the q dot, the derivative of the canonical variable, will always give you some sort of momentum. Sometimes it will be a momentum you can recognize, sometimes it will not. But in this case, it gives us the angular momentum. The next step, we take this very thing that we just got, this angular momentum, and we apply a time derivative. So we just take this thing and just take a derivative with respect to time, like you normally would. We have an ml squared, that's a constant, so it just passes right through the derivative. We have d theta dot dt, well that just becomes theta double dot. This whole thing, this d by dt of dl d theta dot, is the left-hand side for Lagrange's equation. This is half of Lagrange's equation. The other half is found right here, taking partial of L with respect to theta, where we'll get a negative mgl sine theta. So you just take this thing, take a derivative with respect to theta. Again, you're treating theta and theta dot as separately, so this one has a theta, this one does not. And so we'll end up with a cosine going into a negative sign here. So that is the right-hand side. I know Lagrange's equation, it kind of looks very abstract and esoteric, but it always gives you a nice practical result of an equation for the right-hand side and an equation for the left-hand side. Now we're ready to set those equal to each other. So Lagrange's equation is just going to be this thing equals this thing. We can start canceling some things out, and we'll have an ml squared theta double dot equals a negative mgl sine theta. I can cancel those m's, I can cancel some of the l's, and you'll end up with this for the equation of motion, theta double dot equals negative g over L sine theta. So that is technically where Lagrange's equation ends. As soon as you end up with the highest order derivative equal to something involving everything else, that's where Lagrange kind of leaves you off and hopes that you can solve that differential equation. This particular differential equation we cannot solve. I cannot find a theta as a function of time that will satisfy this differential equation. I can find it if I take the small angle approximation where sine theta is approximately equal to theta. Then this just becomes a simple harmonic oscillator. But for larger oscillations, I have to treat this thing computationally. I have to take this and plug it into some sort of numerical method like the Euler-Kromer method or Runge-Kutta or whatever your favorite differential equation solver is. Now before we go, let's take a look at the thing that was confusing me in AlgoDo that I have since resolved, and I'd like to share that resolution with you. I was concerned about what was happening with this magnitude of the acceleration, how it was showing these peaks and then smaller peaks in the peak, and I said, shouldn't this thing roughly be sinusoidal? Well, theta double dot is roughly sinusoidal, but this is not the angular acceleration. This is the full-fledged meters per second squared g-force acceleration, right? This is the acceleration that you would actually feel on a pendulum. I was even on a swing with my kids yesterday, just thinking about what was happening to our acceleration as we were swinging back and forth. The way you can understand it is to go back to the velocity vector here, right? L theta dot cosine theta in the x direction, sine theta in the y direction. We need to take another derivative of this thing, and that's going to require the product rule and the chain rule, right? So the product rule, because I have a function of time here and a function of time here. So I first take a term where I take the derivative of the first piece and leave the second piece alone. So that's real simple. Theta double dot, leave the second piece alone. Plus, now leave the first piece alone, that theta dot, and take a second derivative of all this stuff inside. Well, cosine theta will become negative sine theta will become cosine theta, but then I need the chain rule again. So I'm going to spit out another theta dot, so I have a theta dot squared multiplying everybody. So what I decided to do here was collect all of the x components together and all the y components together. So I have the big x component and the big y component. You might notice there's a nice symmetry there. I have a theta double dot, theta dot squared, theta dot squared. The only difference is where the sines and cosines are, right? That's what happens every time you do vector components and trig functions and derivatives, is that the sines and cosines just flip around who is where. It's real easy then to take the magnitude of this thing, because I can just do Pythagorean theorem. So I take this x component squared, the y component squared, add them together, put the whole thing underneath the square root. And so it is no surprise that this thing shows some interesting features, because remember, this theta is an oscillating function. It might be a good approximation to call it a cosine, or it might not, but theta is oscillating. And then I'm taking a trig function of that oscillating function. So I've got an oscillating function of an oscillating function. Then I'm multiplying it by more oscillating functions, squaring the whole thing, adding them together, square rooting all of that. It's a wonder this thing is even recognizable by the end of that mathematical treatment. So yeah, so I fully expect that this thing should show some interesting behavior, and we will try this out in our pendulum code to see if we can recreate what we saw there in AlgoDo.